Yo, welcome back to my genetics summary video. Today we're still going on chapter 2, but now we're going into a fun little thing that a lot of students love so much, and that's probability rules. Yay! And the reason why people love it so much is because there's a lot of math. Okay? So let's get started on. The first rule, and we've actually seen some of these rules before in my previous videos, but to just summarize what the product rule is, the product rule, you're going to use this. So you're going to use this to calculate the probability of a specific combination of two or more independent events. So the way how you can think about this is we sort of covered it before, where if you had a 1/2 chance from the law of segregation to get either big A or little a, 1/2 chance for that too, and you wanted to figure out what the probability of getting big A is, it's essentially where, because we want a specific combination of big A, we would have to multiply the two independent events together. So to get big A is 1/2, and to get the other big A is also 1/2, so it'll be 1/4. So, and this is a situation where we would use the product rule in this situation. Cool. So here's another good one. We haven't used this one that often, and it really isn't used that often either, but it's called the sum rule. And what you're going to use this for, so you're going to use this to calculate a frequency. You're going to use this to calculate a joint frequency of multiple outcomes that have alternative pathways. So basically what this means is, if we go back to a monohybrid cross, which is just big A, little a, crossed with big A, little a, if you remember from way back in the beginning where we've talked about these crosses, we've already talked about big A probability, which is just 1/4. To get big A, little a in this situation is also 1/4, big A, little a. Same thing over here. And then you would have a 1/4 chance to get little a, right? So the way how you're going to, or the purpose of the sum rule is when you have two identical frequencies, such as big A, little a in this situation and big A, little a here, you would add them together to find the joint frequency, because there's two different pathways that make big A and little a. So basically you would add them together and you would get the actual true frequency of big A, little a, which is just 2/4 big A, little a. Okay? So pretty simple. And you're going to use these rules for a majority of genetics and a majority of problems as well. But here are some practice problems that I've sort of copied and pasted from the textbook, and we can do them together. So galactosemia, and we can refer to this as G, is a recessive human disease that is treatable by restricting lactose and glucose in the diet. So Susan and her husband are both heterozygous for the galactosemia gene. So basically from this information, what we have here is a monohybrid cross where both individuals are heterozygous. And because galactosemia is a recessive human disease, therefore you would have a 1/4 chance to have galactosemia. In other words, what their genotypes are is, so the mother is, let's say, big G, little g, and the dad is big G, little g. You would have a 1/4 chance to get little g, which is what we're looking for. Okay? And then you'll also have a 3/4 chance to get an individual that is normal in phenotype. Okay. So then the question is asking you, what is the probability that none of their children will have galactosemia? So in other words, what is the probability that all 4 of their children, I think, yes, 4 children will have galactosemia? So because we want a specific combination of normal, 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 and normal, what it'll be 3/4 times 3/4 times 3/4 times 3/4. If you are comfortable with math, sometimes this will be referred to as, sometimes this will be rewritten as 3/4 to the 4th power, because repeated multiplication is written in exponential form. So what you can do here is just write it down as 3/4 to the 4th power. So just as a little sidebar. So that's all you have to do for that problem. For part B, essentially the same thing, but they're looking for a combination that is first 2 will have galactosemia and the second 2 will not. So they would be G, normal, normal. So galactosemia, normal. So it's essentially 1/4 times 1/4 times 3/4 times 3/4. Or in other words, you can write this down as 1/4 to the 2nd power times 3/4 to the 2nd power as well. Cool. That's all you have to do for part A and part B. So then we get to a point where the question is asking you, regardless of order, and typically this is a sign that you should use the sum rule, because remember what the sum rule is used for? It's used to calculate a joint frequency when you have multiple alternative pathways that get to the same exact outcome. So what you have to do is you have to figure out what are the possible pathways that you can have where you have 2 children that have galactosemia and 1 will not. So pathway number 1 will be something like where you have both of them having galactosemia at the beginning, and then you have 1 normal kid. The second one would be you would have galactosemia, normal, and then you would have galactosemia. And then the last one would be normal, galactosemia. So what we need to do is we need to figure out the probability of us getting this outcome first, okay? So to get this outcome, it's essentially 1/4 times 1/4 times 3/4. So essentially, let me find what the probability of that is. I think it's better to be written down as a fraction, to be honest. So 3 over 64. So that is pathway number 1. And with this rule, you always have to make sure that all of your pathways are going to be equal. So in this situation, pathway number 2 has the exact same probability, where you would have 1/4 multiplied by 3/4, 1/4. So it's essentially the same probability, 3 over 64. And then same thing for the last one as well, 3 over 64. So basically, right now, in order for us to figure out, regardless of order, probability, we just essentially add them all together. So then our final answer will be 9 over 64. Another way how you may see this written down is repeated multiplication or repeated addition is written down as multiplication. So the other way how you can write this down is basically 3 over 64 times 3. Because you're adding it 3 different times together. Okay, so the next one we're looking at, this is a really tough one where a lot of people struggle on. There's 2 ways how you can solve this question. And both of them one of them is really, really short and one of them is extremely long. So we should tackle the one that is the shortest first, because I think that one is a little bit more practical, especially for an exam. So you have 4 children, and the question is asking you, figure out what the probability of you having a child that, at least one child that has galactosemia. So how can we figure this out? We can do the hard way after, but one of the faster ways how you can do this is to figure out what that is equal to. We can just simply subtract that by the amount of individuals, by the probability of you having individuals that are completely normal. So basically what I mean is, let's say this is equal to x. To figure out what x is equal to, you just do 1 minus the probability of all normal individuals. The reason why we're doing 1 minus that, 1 minus the probability of all normal kids, is because these normal kids do not have the galactosemia trait at all. And because if we have just a single individual that has galactosemia out of 3 or out of 4, we start to have a situation where we have, and after the fact, all of them will have at least one galactosemia trait. So what we can use this is we can simply just cut out all the extra hard work for no reason. So basically, and hopefully that makes sense. If not, just let me know in the comments. So x, 1 minus the probability of you having completely normal, which is 3 over 4 to the 4th power. And that'll be your answer. So, and unfortunately I haven't written it down over there, but it's okay. So how do we figure out this the long way? What we need to do is we need to figure out the possible combinations that we can have at every single time point. So what we can have is 1 galactosemia, we could have 2 galactosemia, 3, and then 4. So basically what I've written down here is that you can have one person that has galactosemia out of 4, 2 out of 4, 3 out of 4, or 4 out of 4. So with this one, 4 out of 4 individuals that have galactosemia, this one's fairly simple. It's essentially 1 over 4 to the 4th power. Right, because there's the only possible combinations of you getting galactosemia is just 1. Okay? So this is a part of the problem where we have to use something called Pascal's triangle. So if we go back all the way from the beginning, this is Pascal's triangle, and this is the exact purpose of using the Pascal's triangle, where you're trying to figure out the probability of you getting a specific combination, or excuse me, a combination that is regardless of a specific order. And the way how you're going to interpret this triangle is that typically, sometimes the things on the left over here aren't written down, but typically it's from top to bottom, where you have 0 number of events, and then you go from 1 to 2 to 3 to 4. Because we have 4 different, children that we're looking at, we're going to be using this 4th event over here. Okay? So, all the way at the beginning where you see this 1, this basically means that you would have the trait that you're looking at, let's say galactosemia, is not appearing at all in this out of 4. So what this 1 means that you have one possibility that you can have normal, 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 normal. Okay? This over here, on the other hand, means that you have 4 different possibilities where you can have galactosemia, normal, 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 and so on and so forth. This one over here on 6 basically means you have 6 possibilities where you can have 2 galactosemic children and 2 that are normal children. And then so on and so forth. The 4 over here means that you would have 3 galactosemic and then 1 normal. And then the one at the end means that you have all galactosemic children. Okay? So what we're going to use is we're going to use this as our indicator by how many different possible alternative pathways give us the specific outcome that we're looking for. Okay? So like I said, this one is 4, this one is 6, and this one is 4. So with this situation where we only have 1 galactosemic children, it's 1/4 multiplied by 3/4 to the 3rd power. This situation here, it's 1/4 to the 2nd power, 3/4 to the 2nd power. And then this one I'm running out of space. It's 4 times 1/4 to the 3rd power times 3/4. Okay. So let me take some time to calculate all this. So this one is equal to 0.42. This one's equal to 0.211. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . 0.004. And then this one on the bottom is equal to 0.004. So what you can do now is you can add these together, because these are different alternative pathways that we can get to answer our question, which is having at least one child. So these are equal to 0.422 plus 211 plus 0.047 plus 0.04. It's around, if we add these together, it's around 0.684. And then if we calculate this answer that we got here, they should be equal to one another. So around 0.684. So these are two different ways how you can solve this problem. And that's pretty much it for that. And then there's a trick question that I've put up over here. If the couple has another 4 children, what is the probability that their next child will have galactosemia? So this answer is actually just 1/4. The reason why it's 1/4 is, imagine if you had a coin flip that you've been doing a couple hundred times so far. What is the probability that your next coin flip will be, a heads? It doesn't matter how many times you've done a coin flip already. The probability of you having a heads in the next try will just be 1/2. So the answer will be 1/4. So hopefully today, hopefully this kind of helped out with how to use the triangle, how to use Pascal's triangle, and how to solve some practical genetics problems. So hopefully today was helpful. Yep. All right. See you guys later.